Okay, so let's do the part 5. So now we are in a visible scale right now. That we're gonna talk about the state of matter. The state of matter that we care about is liquid, gas, and solid. There is something called the plasma, but we don't care about that one. So the liquid, for example, if it's a water, it's 18 gram. So 18 gram is probably about this is about 18 gram by volume of water. But if you're dealing with the 18 gram of water, then what will happen is that if it's in a gas phase, then what you have is that this one right here is 1 liter. So you have 22 bottle of this volume to actually create is needed to actually contain 18 gram of water. 22 of these. The liquid is only like this much, right? You need 22 of this. That's huge. So the volume of gas is huge, volume of liquid is small. The solid is pretty much the same stuff. The 18 gram of ice cube, that means it's just about this, maybe slightly more. So if I actually maybe loosen up the cap, that's just about the volume of the ice. So no change to the liquid, it's very small. So the gas occupies a large volume, liquid and solid very small volume. That's what you need to remember. Then getting used to the SI unit is kind of important, so what I want you to do is just remember this particular table right here. Meter, kilogram, second, that's about it. And then mole, Kelvin. Yeah, we don't care too much about ampere. We don't care about that or this. So we care about that one, that one, that one, that one, that one. Okay? So to actually determine this SI unit, now people went actually a long way to actually determine how accurately you can actually determine the meter, how accurately you can determine the second, and so on and so forth. So meter is defined by the speed of light. 1 divided by 299,792 299,792,458 of the distance that's traveled by speed of light. Divided by that number is the meter. Is that right? Yeah. Traveled by the 1 second of the distance covered by the light. And then time is defined by whatever the things that's written in here. It's not important. And if you're talking about mass, I think it's already changed, but you can actually take a look at this video right here. It's kind of interesting. None of this is important, so you can actually skip if you want to. The Kelvin right here is defined by the triple point of the water. It's Kelvin is a fraction of the triple point of water. The fraction is that much right here. So yeah, if you are interested about these type of things, then Google it. Then there's a whole bunch of information that's available on the internet these days. So far we are actually talking about this atom molecule, formation of molecule, right? But we never did the chemical reaction. So the chemical reaction, to me, it's again, it's a displacement of the atoms. Relative position changes before and after the reactions. That's pretty much all there is to it. So what happens if you mix something together? It may cause a chemical reactions, yeah. And chemical reactions, you have, before the reaction you have reactant, after the reaction you have product, and then state symbol could be solid, liquid, and gas, or AQ. AQ is the stuff that's in the water. The AQ is kind of special because that we have so much of water around us. So we write the chemical reaction in the following way, like this. Like this. Reactant is usually on the left hand side, product is on the right hand side, and then you have this arrow that's pointing this way, right? And notice that you have double arrow here. That means that reactant is going this way to form the product, but product also wants to go back to the reactant. So it's like two different ways always happening. Alright, so balancing the equation is probably the most important things for this chapter right here. So you have this H2 plus O2 is becoming the H2O, right? So H2 mixing up with the O2 is becoming H2O. Do you notice there is something wrong here? Number of hydrogen 2, number of oxygen 2, number of hydrogen 2, number of oxygen 1, right? So you're not balanced, right? You're destroying the oxygen right here. So that's not good. So you're gonna have to balance these things. How do I balance that? Let's just do this one right here. So oxygen, I have 2, right? Right here. Then if I actually have H2O, it contains only 1 oxygen, so I have to have 2 oxygen right here. Right? Then because I have 4 oxygens on the right hand side, I have to have 2 H2, which contains 4 hydrogens, right? That way you're going to balance the whole thing. 2 hydrogen plus 1 oxygen becoming 2 H2O. Now this one you're gonna need quite a bit of practice. So let's just dive into something that's a little bit more complicated. So what I want you to do is to pause the video right here and then try to figure out how to balance these things. Key stuff that you have to achieve here is that number of atoms before and after the reaction, number of each type of atom has to be conserved. So if I start out with a 10 carbon, then you're gonna have to end up with a 10 carbon at the product too. So pause the video right here and then just try to do the program. Alright, that's good. Now you have tried your way of doing it. Now I'm gonna try to tell you how I'm going to balance these equations here. What I actually do is that I usually work out with the atom with the rarest species. the rarest means that how many times it's going to show up. So for this particular case, I have carbon shows up only one time on the left hand side. It shows up only one time, right? And then carbon shows up on one time on the right hand side. Hydrogen is going to show up one time on this side and then one time on that side, right? But oxygen shows up one time here but two times here, right? So according to my definitions, oxygen is not the rarest. So we are not going to start out with oxygen. We forget about oxygen for now. And then carbon or hydrogens. So let's just start out with carbon here. Generally speaking, hydrogen is the later part. So the rarest species right here is going to be carbon. So carbon, I have 6 carbon on the left hand side, right? You see that? I have 6 carbon on the left hand side, right? Then I have to have 6 carbon on the right hand side. How do I do that? I actually have 6 here. It's good. That will balance the carbon, right? Now next up, next rarest is hydrogen, right? Remember that oxygen shows up like twice on the right hand side and then hydrogen shows up only once, right? So oxygen is not the rarest. It's the carbon or hydrogen was the rarest, right? And we're done with the carbon. We're going to move on to hydrogen. Now hydrogen, I have 14 carbon on the left hand side, 14 carbon on 14 hydrogen on the left hand side. Then I have to have 14 hydrogen on the right hand side too. So how many, what do I need to do? I have to have 7 H2O, right? The 7 H2O means that I have 14 hydrogens, right? So the hydrogen is now balanced too. Now let's just do the oxygen right here. Oxygen, I have for this side it's complete, right? The right hand side is already complete. So how many oxygens do I have? 12 oxygen plus 7 oxygen. So total of 19 oxygen, right? Then I have to have 19 oxygen too on this one. So 19 divided by 2 is going to do the job, right? 19 divided by 2 multiplied by 2 is going to give you 19. So it's the total of 19 oxygens on the left hand side as well. So the whole thing is balanced. Now I'm going to give you the full credit out of this one too, but it's most of the time that students like to use the whole number here. So for that, you just multiply everything by 2 to get that. There's something wrong with the 18 here. So what did I say on this one right here? The 14, right? Okay, so that's good. You want to fix that things in the PowerPoint too later on. Alright, then the very last slide that for this particular thing is practice problem. This is going to be difficult, but it's what I want you to do is to figure out how to do these problems. So you have 300 milliliters of pure HCl. So in chemistry problems, you always go back to the number of mole, not the volume, the number of mole. The reason why that I want to stay with the number of mole is that all of these guys, the 7, 6, 19 over 2 or 1, or 14, 12, 19, or 2, all of those are represented by number of moles. So that means that everything that you see in the chemical formulas are represented by number of moles, right? So in chemistry, you always want to count the number of moles first. So 300 milliliters, I need to convert this one to the number of moles. How do I do that? I have to convert the volume to the mass, and then mass to the number of moles. And once you figure it out, then you can actually figure out the this particular question right here. So let's do this one. So I have 300 milliliters, and then I have 1.49, that's the density, right? Density is 1.490 gram per milliliters, right? So every milliliter weighs 1.49 gram, and you have 300 milliliters, right? Then what is the mass? What is the gram here? The gram here. That's simply multiply, right? Multiply 1.49 multiply by 300, right? So you have 447 gram. So what is the molecular weight of the HCl right here? The molecular weight of the HCl, I gotta go check out the periodic table. Where is that periodic table? Oh, yep. I know the H, but I don't remember the chlorine. So chlorine right here is 35.5. 95.45 is the mass of chlorine, and then 1 is the hydrogen. That's a gram per mole, right? No, maybe that gram per mole for chlorine, gram per mole for hydrogen, right? So HCl, gram per mole for HCl is simply adding these two, right? This plus that. That's 36.45. So how many moles are in this 447 gram mole of HCl? That's simply 447 divided by 36.45, right? So I have 12.26 mole of the HCl. Alright, then how many mole of Cl atoms? Each HCl contains 1 mole of Cl, right? So it's exactly the same here. So that's that, right? Now out of this, what was the question? I forgot the question right here. The 75.8% is 35, right? Chlorine 35. 75.8. So this number multiplied by, did I say 75.8? 75.8, yeah. So 0.758, right? That's the number of mole of 35 Cl. That's 35 Cl. 35 is the isotope, right? So it's confusing, but sorry, it's a 35 isotope. maybe I should say 35 isotope. Then each isotope weighs 35 grams, then I just need to multiply this number by 35, you get a gram. And that's pretty much the answer here for this particular problem.